Hey everyone, and thank you so much for bringing our engineering team in today. Let's dive right into this explainer. We're here to walk you through our proposed automated safety barrier system designed specifically for your manufacturing plant. Look, as your operations expand, the intersection of human and machine traffic becomes the absolute most critical point of vulnerability on your floor. We've designed a sequential control system that literally guarantees safety without bottlenecking your production. Today, we're going to show you exactly how the engineering behind it works.
So, I want you to picture the busy, intersection-heavy reality of your own manufacturing floor right now. You've got these automated guided vehicles, your AGVs, moving incredibly heavy materials all around the facility. But you also have your team, your pedestrians, walking those exact same corridors. And industry data shows us that vehicle-pedestrian intersections account for a massive percentage of plant floor incidents. The stakes here are incredibly high. So how do we safely and instantly manage traffic when a 2-ton automated vehicle meets a pedestrian walkway? We can't just rely on human reaction time. We need an automated system that is absolutely flawless, highly robust, and instantaneous.
Here's our quick roadmap for today. We'll cover the plant safety challenge, the logic brain using the Mealy model, our synchronous clockwork design, our asynchronous quick reflexes design, our real-world simulation proof, and finally securing your plant's future.
Section 1. The Plant Safety Challenge.
Okay, let's look at the exact hardware inputs and outputs. These are essentially the eyes and arms of the entire system. We place 2 proximity sensors, we'll call them S1 and S2, on either side of the walkway to detect when an AGV is approaching. Our primary output here is Z. When Z is triggered high, the physical barriers close immediately to protect the pedestrians. But, a truly smart system talks back to the vehicle's right, so we also integrated 2 telemetry signals. ZL tells the system an AGV is moving left to right, and ZR tracks movement from right to left. This basically ensures the AGVs know for sure that the barriers are securely down before they even try to cross.
Section 2. The Logic Brain. Mealy Model.
We actually based our entire software architecture on a concept known in computation theory as a Mealy machine. You can kind of think of a Mealy machine as a highly alert traffic cop. Instead of just blindly following a set protocol based on their current status, this traffic cop makes decisions based on both their current state and exactly what they see happening right at this very millisecond. In engineering terms, our output values are determined by both the current state of the system and the real-time inputs coming from those S1 and S2 sensors.
Now you might be wondering, why didn't our team just use the other really common finite state machine, the Moore machine? Well, in a Moore machine, the output depends only on the present state. That means it actually reacts one entire clock cycle slower to new inputs. A Mealy machine, on the other hand, places its output directly on the transition. It reacts instantly to current input. Plus, a Mealy machine requires fewer states and a lot less hardware to actually build the circuit. So the big takeaway here is this. When a 2-ton vehicle is barreling toward a human walkway, split-second reflexes are non-negotiable. Waiting one extra clock cycle for a barrier to close is a massive safety risk. We completely eliminate that risk by going with the Mealy design.
Let's translate all that abstract math into a physical sequence of events on your plant floor. We went ahead and mapped out every possible state. Step 1, the system is chilling in an idle state. An AGV enters from the right, triggering sensor S2. Bam! Instantly, the barrier output Z closes. Step 2, the system just waits. Once the sensors confirm the AGV is fully passed through, the system transitions back to idle and the barriers open up again. Step 3, let's say an AGV enters from the left this time, triggering S1. The system recognizes this is a completely different transition, but it perfectly executes the exact same safety protocol, snapping those barriers closed. This Mealy logic basically guarantees that any presence of an AGV keeps those barriers absolutely locked down.
Section 3. Synchronous Design. The Clockwork.
I want you to think of the synchronous system as incredibly reliable clockwork. It uses a master clock pulse to ensure highly predictable transitions. For state memory, we utilized edge-triggered JK flip-flops, and to make the circuit as efficient as humanly possible, our engineers minimized the states using Carnot maps. But honestly, the biggest advantage here is the tracking. Because this system is clocked and moves through very clearly defined states, it is perfectly suited for tracking complex directional telemetry. It flawlessly generates those ZL and ZR signals we talked about, meaning your AGVs always know exactly which direction traffic is flowing. That virtually eliminates any chance of a head-on collision.
Section 4. Asynchronous Design. Quick Reflexes.
Now, if the synchronous design is a perfectly ticking clock, our asynchronous design is pure reflex. It is entirely unclocked. Here, the feedback isn't governed by clock signals at all. Instead, the circuit output is directly linked to the sensor inputs, using very basic combinational logic. We're talking just simple AND, OR, and NOT gates. If sensor S1 or sensor S2 trips, that barrier closes immediately. It bypasses the complexity of flip-flops entirely to trigger the safety barrier the literal millisecond its sensor is activated.
So let's break down the engineering trade-offs between the two. The synchronous design is extremely predictable and robust because of those JK flip-flops. The asynchronous design, on the other hand, is instant, using just basic logic gates. But here's the catch with asynchronous. If we try to force it to track direction, to handle those ZL and ZR signals, it requires adding a bunch of complex memory elements or pulse detectors just to track the exact order the sensors were activated. And as our testing showed, making an asynchronous system track direction makes it overly complex and really prone to transient glitches. So while asynchronous is super simple and fast, synchronous is vastly superior for those complex intersections where you absolutely need directional communication with the vehicles.
Section 5. Real-world simulation proof.
We didn't just map this out on a whiteboard. We built and tested both of these circuits rigorously using Proteus simulation software. We wired up the flip-flops, used push buttons to simulate your plant sensors, and mapped the outputs right to digital oscilloscopes and LED indicators. Actually, I love this raw quote from one of our automation engineers during a really successful test run. See, the O's are blinking here? These are the output results for red LED. That blinking light? That is absolute mathematical proof that our Mealy logic works dynamically in real time. When the digital AGV hit the sensor, the barrier logic triggered flawlessly. Every single time.
So why the number 2 here? Because it represents those two absolutely critical telemetry signals, ZL and ZR. In our Proteus simulations, the synchronous circuit successfully transmitted these two directional signals back to the approaching AGVs without fail. Remember, it's not just about closing a physical gate, it's about closing the entire communication loop between the barrier and the automated vehicles themselves.
Section 6. Securing your plant's future.
All right, so here is our final recommendation for your facility, a hybrid deployment. For your main corridors, the ones where AGVs are moving in multiple directions and desperately need telemetry feedback, deploying the synchronous design is going to give you ultimate glitch-free reliability. However, for those secondary, maybe one-way pads where you literally just need a simple open-close barrier, our asynchronous logic offers a really highly responsive, lightweight alternative. In both cases, the Mealy logic brain ensures absolute pedestrian safety without unnecessarily halting your operational flow. Bottom line, it's safe, it's efficient, and it is ready to deploy.
By implementing this system, you guys are taking a massive step forward in overall plant safety. But I want to leave you with this slightly broader challenge today. If our engineering team can make your physical safety barriers think this fast, communicate directionally, and operate this reliably, what else on your manufacturing floor is ready for an automated upgrade? Thank you so much for your time today, and we're super excited to answer any questions you might have.